Welcome to another Mythology video. Today I'll animate some absolutely gorgeous visual shrink proofs for you. Really nice, super accessible and at the same time deep mathematics. Plus at the end I'll prove some really cool irrational trigonometry for you. Something you may have always felt in your bones but never captured in words. But what's that? You've never heard of a shrink proof? Well, I've actually shown you some in previous videos, but don't worry, all will be explained. Ready for a fun journey down a very deep rabbit hole? Okay, here we go. First, to motivate things and to get you hooked, here's a little puzzle. Take a look at the grid of dots over there. How many squares can you make with all four corners on the dots? Well, plenty of you will be familiar with puzzles like this. Of course, it's easy to spot lots of squares, but unless you're very systematic, it's really easy to overlook a few and you're bound to get it wrong. Shall we count the squares together? Systematically? Okay, there is this 4 times 4 square. Then there are the 3 times 3 squares. How many of those are there? Well, 1, 2, 3, 4. Okay, next are the 2 by 2s. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. And finally, there are the 1 by 1s. How many? It's not hard to guess, right? 1, 4, 9, so what's next? Yep, that's the squares. So a good guess is that 16 is next. And of course that's true. And so the total number of squares is 1 plus 4 plus 9 plus 16, which is 30, right? Wrong. And this comes as a bit of a surprise when you first see it. What did we miss? Well, there are lots of tilted squares in this grid, like this one or that one. Now, first challenge for you, complete our count. Systematically, of course. How many squares are there altogether, including the tilted ones? And for the super keen among you, can you find a formula for the total number of squares in an n times n grid? As always, leave your answers in the comments. Okay, time for the next puzzle. How many equilateral triangles are there in this grid? Even the puzzle nuts among you may not have seen that one before. So how many equilateral triangles can you spot in the grid? That's a tough one, isn't it? Not obvious at all. Now, how can we systematically look for such triangles? Well, we can just scale and move the red triangle so that 2 of its vertices end up on dots, like this, okay? And then we just have to check whether the third vertex is also on a dot. And nope, not in this case. Let's just do this a couple more times to build some intuition. So there, doesn't work. That one, nope. That one, not even close. What if we start tilting like this? Nope. And no. Time for a prediction? Now by now, a lot of you will have probably begun to suspect that there are no equilateral triangles at all in this grid. And you are right. No equilateral triangles in there. So then, what if we start with a larger grid of dots? A pretty natural question to ask, right? And being mathematicians, let's just go all the way and ask, are there equilateral triangles in the infinite square grid? So if the grid goes on forever in all directions, are there any equilateral triangles? You can probably guess, but the first mathematician to ask a question to prove the answer was the French mathematician Édouard Lucas in 1875. You may have come across his name before. The important relatives of the Fibonacci numbers, the Lucas numbers, are named after him. There. 2 plus 1 is 3, 3 plus 4 is 7, 4 plus 7 is 11, etc. This sequence grows just like the Fibonacci numbers, except the sequence starts with 2 and 1 rather than 2 ones. Édouard Lucas is also the inventor of the Tower of Hanoi puzzle. You know that one? And he was the first to publish a description of the well-known game Dots and Boxes. I played it when I was young. Anyway, enough game playing, back to our triangle hunt. Yep, back to the hunt. And first, one important and easy observation. We can find triangles with vertices on the grid points that are really, really, really close to equilateral triangles. Why is that? Well, let's suppose that our grid has tiny spacing of, doesn't really matter, 1 millimeter. Okay, now take a huge equilateral triangle with, let's say, 1 kilometer sides. Okay, now toss the triangle however you like onto the grid. It's like a carnival game, and you're trying to have all 3 vertices of the triangle hit the dots. Will you succeed? Of course not. No one ever wins at carnival games, but you will get very, very close. Well, perfect for getting you to pay for another toss, right? So, because of the tiny grid spacing, each vertex will be no more than 1 millimeter away from some grid point. So we can just deform our huge equilateral triangle just a tiny little bit by moving each vertex to its closest grid point, like this. Okay? This new triangle will be pretty much indistinguishable from an exact equilateral triangle. Right? You can't tell the difference, even with this much smaller setup. And in this way, by making the beginning equilateral triangle larger and larger, we find triangles with vertices on grid points that are as close as we like to being equilateral. But of course, close doesn't win the game in carnival games or mathematics. The fact that these ultra-close approximations exist does not prove that there are exact equilateral triangles hiding in the square grid. And in fact, there aren't. Edward Luca proved the surprising fact that there aren't any equilateral triangles there. Again, that happened about 150 years ago. Luca's proof over there was very pretty, but algebraic. What I want to show you instead is a visual proof, the methodologization of a really amazing proof by the mathematician Joel Hampkins that he posted on his blog in 2016. If you've got mathematics in your blood, then I guarantee this stuff will make your day. Okay, to set up the proof, we'll give 2 simple properties of square grids. For the first property, connect any 2 of the grid points with a segment. And color the endpoints of the segment blue and green. There. Now turn the segment 90 degrees around the blue end, and the green end will land on another grid point. Easy to see, right? Same thing if you turn around 180 degrees or 270. That's our turning property. Here's how we can use this property. Let's say somebody tells us that 2 dots are part of a square grid, right? Then we can use the turning property to discover other points in this grid. There, that's another point of the grid, and that's another one, and another one. Got it? Great. Now for our second property, which I'll call the shift property. Start again with 2 points in the grid. So same guys. Grab the segment and shift the segment so that the blue point ends up at another point of the grid, like this. Okay, zip over. Then the green point will also wind up at a point of the grid. Now let's just do this one more time. Okay, shift over. Again, the green point coincides with a point of the grid. Pretty obvious, right? Just like for the turning property, we can use the shift property to capture points of a mystery square grid. As an example, say we know that those 3 points over there belong to a square grid. Then here's how we can find another point of the grid. Right? Just grab it and shift like that, and we found another point. All clear? Piece of cake. Okay, let's get to work. Let me show you why there are no equilateral triangles in the square grid. Let's assume what we see over there is an equilateral triangle with all 3 vertices in some square grid. Now, important, we have no idea whatsoever what that grid might be, its spacing or how it might be rotated. All we know about the grid is that the 3 triangle vertices are grid points. But using our turning and shift properties, we can capture some more points. And this will be important for later, so remember it, okay? Note that for the moment, we'll only use the shift property. Okay, time to begin our hunt. That's kind of cool, isn't it? This means that if a square grid contains an equilateral triangle, then it also contains a regular hexagon. Okay, let's keep on going and pin down some more points of the grid. Remember, so far we've only used the shift property, but now the turning property kicks in. All we'll need are 90-degree turns, and here we go. This means that if a square grid contains a regular hexagon, then it also contains a smaller regular hexagon. And at this point, are your mathematical spider senses tingling? No? Well, keep watching. Got it now? We've created an incredibly shrinking nest of hexagons with all their vertices on our square grid. But of course, that's completely impossible. Think about it. No matter what the spacing of the grid is, eventually the hexagons will be too small to reach from grid point to grid point. Right? There, no chance. So where does this leave us? Okay, so mathematicians may do some astonishing things, but we're still not allowed to do the impossible. We can't really make that shrinking nest of hexagons. But those hexagons all came straight from the assumption that our square grid contains an equilateral triangle. And so that assumption just cannot have been true. The grid could not have possibly contained an equilateral triangle. And that's the proof. A beautiful proof by contradiction. Absolutely marvelous, isn't it? Of course, along the way, we also showed that there are no regular hexagons in the square grid. So what about the other regular polygons, pentagons and heptagons and octagons and so on? Well, exactly the same argument allows us to show that all the remaining regular polygons also cannot occur in a square grid. All we get are squares. For example, here are the shrinking regular pentagons that do the trick. Okay, to summarize, square grids do not contain any regular polygons, apart from squares, of course. End of story? Nope, just the end of the chapter. Time for another puzzle. We'll return to our incredibly shrinking polygons in the plane soon, but first let's do some cheating. Let's add a dimension and see what that gives us. That's a 3 by 3 by 3 cubical grid. I've drawn in the struts since without them the grid is pretty confusing. Pretty damn confusing, right? Can't see the 3D at all. Anyway, time for more puzzles. You know what I'm going to ask, right? Yep. How many squares are in this 3 by 3 by 3 grid? And then, how many equilateral triangles, regular pentagons, regular hexagons, etc.? I'll leave figuring out the number of squares as a challenge for you in the comments, right? What about the other regular polygons? Anything in here or in the infinite cubical grid? Well, doesn't look very triangly, does it? But have a closer look. Yep, those three corners of one of the cubical cells are the vertices of a perfect equilateral triangle. Why? Well, because the three edges are diagonals of faces of that cubical cell, and of course all these diagonals have the same length. But since there's an equilateral triangle in this grid, wouldn't the shift property then give us a regular hexagon, just like in 2D? Yep, and here it is. Nice, huh? Remember what happened last time? So won't the turning property now allow us to create a smaller hexagon in the grid and then a smaller one and so forth? Does that mean the equilateral triangle that really is there really isn't there? Have we exploded the mathematical universe? Well, let's try. Aha! It doesn't work. The vertices of the new smaller regular hexagon are not grid points. The mathematical universe is safe. In fact, while the 3D grid definitely has the shifting property, or the shift property, it doesn't have the turning property. But now, what about all those other polygons? Remember, all our proofs by contradiction in the 2D square grid use the turning property to create the shrinking polygons. That doesn't work in 3D. So maybe all of those other polygons are also hiding in the cubical grid. That'd be really cool. And it's not true. Damn. The devil comes to spoil our fun in the form of a pentagon. Have a look at this. Well, that's pretty cool. An Eiffel Tower vanishing inwards rather than upwards. So what just happened? Well, we constructed this sequence of shrinking pentagons just using the shifting property, which, remember, also works in 3D. And so this proves that regular pentagons also don't exist in the 3D grid. The same sort of star argument also works for lots of the other regular n-gons. For example, here's a shrinking diagram proving that there are no regular heptagons in the grid. And here's the one for the regular 9-gon. However, this really cool argument doesn't work for all n-gons. Of course, it better not work for hexagons since they really are there. But it also doesn't work for octagons. See if you can figure out what goes wrong in these cases. In fact, the star argument fails for any regular n-gon where n is a power of 2. But all is not lost. There's a third shrinking argument, again just using the shifting property that takes care of all regular n-gons beyond the hexagons. This argument actually dates back to 1946 and a paper by the Swiss mathematician Willi Schaerer. I only found this one after quite a bit of digging. Now here's an animation of Willi Schaerer's shrinking argument. Enjoy! Isn't that absolutely beautiful? As a pretty easy challenge for you, figure out why Schaerer's shrinking argument fails for the other regular polygons, for hexagons and below. Great stuff, isn't it? Let's summarize what we've got so far. So, the 2D square grid only contains one type of regular polygons, the squares. All right. The 3D cubical grid contains three types of regular polygons: equilateral triangles, squares, and regular hexagons. Not sure whether you're into this stuff, but what about higher dimensions? Nope, nothing new happens there. Since these higher dimensional hypercube grids also have the shift property, everything that we said for the 3D cubical grid remains true. So they contain equilateral triangles and squares and regular hexagon, but that's it. And finally, end of story? No, one more chapter to go. We'll answer a question that was staring at us all through school, but that probably none of us ever asked. Ready to go deeper? Okay, last chapter. Ready for some trick? No, wait, come back. There's no flagpoles or ladders against the wall. You'll really like this one, I promise. This is Willy Scherer's 1946 paper on shrinking polygons. It's very short and, believe it or not, it doesn't contain a single diagram. Amazing, isn't it? Just looking at this, you would never suspect that there is a nice visual proof hiding there. Mathematicians can be really weird at times, and it gets weirder. Scherer says that the only reason why he published his proof is because another Swiss mathematician, his student Hugo Hadwinger, found a really good application for the shrinking argument. And what was Hadwinger's application? Let's keep scrolling. There, in the same journal, right after Scherer's paper, we find Hadwinger's paper entitled Über die rationalen Hauptwinkel der Goniometrie. All clear? What's that? You don't speak German? That's okay, I forgive you. Irgendwann mache ich auch mal ein ganzes Mathologer-Video auf Deutsch, versprochen. Anyway, German or not, there's plenty here that should be very familiar. Up top, there's fractions of 2 pi, and down below, I'm sure you'll all recognize the angles in that list. 0, 30, 45, 60, 90, 120, etc. These are the nice angles that we all know from school. They're the angles that pop up in equilateral triangles and squares and regular hexagons, the sort of regular polygons we've been going on about. The niceness of these angles shows up in other ways as well. Most obviously, these angles are all rational. They're simple fractions of a full circle. But of course, just like there are infinitely many rational numbers, there are infinitely many rational angles. But what makes those particular rational angles especially nice is the trigonometry. Those are the angles for which getting the exact values of trigonometric ratios, sine and cosine and tan, is really straightforward. And there's something extra special about those trig values that you would have always known but perhaps never focused upon. For each of those rational angles above, at least one of the trigonometric ratios is also rational. All rational numbers there on the right. Looks very familiar, doesn't it? And now comes Hadwinger's insight. If we look at Scherer's shrinking polygons in just the right way, Scherer's argument proves that the angles up there are the only rational angles, with at least one of the trigonometric ratios also a rational number. So really just school stuff and something you probably never knew. Definitely it was new to me. Obviously, this is an absolute gem. But unfortunately, Hadwinger's write-up is a bit of a mess. So for you and for posterity, let me present you with a methodologization of Hadwinger's proof. I'll focus on the cosine part of the proof. The proof that the only rational angles with rational cosines are the ones over there, together with these obvious companions. Right? The cosines of all these simple angles are either 0, 1, minus 1, 1/2 or minus 1/2. And the claim is that the cosines of all other rational angles are irrational numbers. That's what we want to prove. Okay, so just as a reminder, a rational angle is an angle of this form. Here P over Q is a non-negative fraction less than 1 in lowest terms. So the integers P and Q have no common factor and P is less than Q. So the fractions in our short list over there are just the rational fractions with Q equal to 2, 3, 4 and 6. So what we want to show is that all cosines of rational fractions with Q equal to 5, 7, 8, 9, 10, etc. are irrational. 5, 7, 8, 9, etc. Notice that these are exactly the numbers corresponding to polygons for which the shift property gives us shrinking arguments. Not a coincidence. Okay, let me show you how the proof works using a specific example. Let me show you that the cosine of the angle 3/8 of 360 is irrational. As you can probably guess, since the proof is based upon our shrinking argument, this will also be a proof by contradiction. So let's assume that the cosine of our angle is a rational number r. Now let's look at multiples of our angle. 2 times alpha, 3 times alpha, 4 times alpha, 5 times alpha, and so on. It turns out, and this is really just high school stuff, that all the cosines of the multiples of our angle alpha can be written as integer polynomials of cos alpha. Above, I've listed the first few of these polynomials. Let's have a look at the very first one. There, that one. Cos of 2 alpha equals -1 plus 2 times cos squared alpha. Well, since we are assuming that cos alpha is a rational number r, that means cos of 2 alpha is also a rational number. Right? If r is a rational number, then -1 plus 2r squared is also a rational number. In fact, in exactly the same way, the other cosine polynomials show that all the cosines of these multiples of alpha are rational. We'll use this fact in a moment. Again, the specific angle we want to focus on is 3/8 of 360. Okay, what's next? Well, if we want to apply our shrinking argument, we better bring in a regular polygon to shrink. The denominator of our angle is 8, and so we start with this regular octagon, centered at the origin of the xy plane and with outer radius 1. Here's our angle. Here's 2 times this angle. And 3 times, okay, and one more 4 times, and so on. Because the numerator 3 and the denominator 8 are relatively prime, we hit all corners of the octagon. Okay, remember, the cosines of all the multiples of our angle are rational. Because we chose radius 1, this is the same as saying that the x-coordinates of all the vertices of our octagon are rational. Now let's make everything integers, right? Rational numbers are good, but integers are better. Suppose all those fractions there have common denominator s, okay? Then scaling this picture by s gives an octagon, all of whose vertices have integer x-coordinates. Let's just do this. Okay, so we scale up, and that makes all those rational x-coordinates into integer x-coordinates. All good? And now all is ready to use shifts to perform the shrinking construction, just as before. So let's just do this again quickly. Do you get it? The x-coordinates of the original octagon are all integers, but because we are using shifts, that means all the x-coordinates of the second smaller octagon must also be integers. All those guys are also integers. And you can see where we're going with this, right? The exact same will be true for all the subsequent smaller octagons. So all the infinitely many colored dots that we come across this way stand for integers. And of course, that's impossible. Since the spacing between the dots shrinks to 0, they can't possibly all be integers. And that's our contradiction. Ta-da! So we've used our shrinking regular octagons to prove that the cosine of the angle 3/8 of 360 is irrational. And similarly, we can use shrinking regular cugons to prove that the cosines of all these general rational angles are irrational. And the sine and tan part of the proof are also easy. Isn't that beautiful? Okay, leave a note in the comments and let me know what you think of all this. Well, and that's all from me for today. Until next time.